Hello everybody, my name is Gustavo and today I will be presenting the work A Reliable and Low Latency Graph Routing Approach for IWSN using QRouting. This presentation will include the introduction, the theoretical concepts and literature review, a brief description of the approach proposed, the performance evaluation, and finally the conclusions and future work. Industrial wireless sensor networks, IWSNs, are used for communication in automation and allow the incorporation of the Industrial Internet of Things, Industry 4.0, and Internet of Things concepts. This market is expected to reach $8.7 billion in the next 5 years, and IWSNs present characteristics such as flexibility, mobility, scalability, low maintenance, and reduced infrastructure required. But also we have some challenges involving the wireless communications, like shared medium, coexistence, interference, signal reflections, attenuation, and so on. Besides, we have applications requiring reliable, low latency, low power, and real-time communications. WirelessHART, ISA SP100.11a, and WIA-PA are examples of IWSN's current protocols and standards. The infrastructure consists of wireless sensor devices. We are going to call them here nodes, connected to a gateway through access points. The gateway provides the connection with the automation network, and this device, called a network manager, is connected to the gateway and is responsible for the overall configuration of the network. These centralized approaches allow better control of the network operation and also reduce the costs of the nodes. Routing is one of the network manager tasks. Usually, IWSNs are mesh networks where devices may act as routers, increasing path availability and network reliability. Graph routing is used. A graph is a route that connects two nodes together in the network to effectively form a chain of nodes to reach some destination. That means that each intermediate node in a route to the destination may have multiple neighbors available to forward data towards the destination. Graphs are built by the network manager and then configured to be used by the nodes. The graph routing algorithms have parameters, often fixed and suitable only for certain network operation conditions. The selection and optimization of these parameters for a given application requires testing and monitoring the network. The user must know details about the algorithms, and this makes it hard to properly adjust them. The routes selected are mostly built trying to reduce latency and energy consumption. Here we have a graph that represents a network topology and the uplink graph, used by nodes to send data towards the gateway. Machine learning has been used for routing, providing a system with the ability to learn and improve from experience. Reinforcement learning is an approach that relies on the existence of an agent that interacts with an environment and receives rewards based on the results of its actions. The agent explores the environment and learns how to behave to maximize its rewards. Reinforcement learning has been used in wireless sensor networks. Decentralized approaches allow nodes to select routes independently. However, this is not possible in IWSNs, since the network manager is the only device responsible for choosing the routes. The existing centralized approaches are not suitable too. The Q-learning algorithm can be used to apply the reinforcement learning concept. It is an algorithm executed periodically in the application. It uses a table with the same size of the number of states times the number of actions to store key values, which are the long-term rewards that an agent can expect to get by taking an action in a specific state. The key values are updated at each iteration using the old key value and the new reward received from the environment. Alpha is the learning rate parameter, which makes the agent give preference for immediate rewards. The agent can adjust its preference for long-term rewards using the discount factor gamma. The action to be taken in each state is chosen through exploration or exploitation. When exploring, the agent selects random actions to extend its knowledge about the rewards. When exploiting, it chooses the action with the best reward. By balancing exploration and exploitation, the agent increases the rewards received over time. One of the approaches to balance exploration and exploitation is epsilon greedy, where the agent explores with a probability all available actions in a state, and sometimes it exploits the best available action. The rewards are defined during the project time and usually represent some value based on the improvement of some performance metric in the environment. The network manager has a sequence of tasks that are executed when the topology changes, when the network configuration changes, or periodically for optimization. Network Manager uses updated information of the network topology, nodes, and operation conditions to run these tasks. The routing algorithms are first executed. Then, the scheduling algorithms translate the routes in a sequence of time slots used for communication. These routes and links are then converted in a sequence of commands sent to the nodes to update the network configuration. Command overhead is reduced by comparing the old and new routes and links and only updating the changes. More information about these procedures are available in the paper and in the references. So, the main contributions of this paper are the QLRR-MA approach, the algorithm description, and the discussion of the use of reinforcement learning for routing in IWSNs. The comparison of the approach with the state-of-the-art routing algorithms, the methodology for comparison, and the evaluation of the approach in an IWSN simulator are also contributions of this work. So, our approach will be called Q-Learning Reliable Routing with multiple agents. It will run periodically during the routing construction task of the network manager, as I said before, and it will use current topology information and measurements and also learning information stored in the memory of the network manager to build an uplink graph. We use three baseline algorithms to build our approach. The HAN algorithm, which is a greedy algorithm that builds the uplink graph by adding node by node and choosing two neighbors, which we'll be calling successors, that the node will use to forward data towards the gateway. We also use the ELHFR algorithm, which evaluates a breadth first tree level for each node. And also we use the Q-routing algorithm that defines that the state is a destination node and the actions will be the next hop neighbor available to forward data. In this picture, we can see the greedy approach used, where each node is added to the uplink graph iteratively until all nodes are added. In our approach, each node will be represented by an agent inside the network manager. When a node is being added to the uplink graph, its agent will be requested to take an action, choosing its successors. That means it will choose to which neighbors this node will send information. Each agent will take then this action according to the Q-learning algorithm. The graph construction finishes when all available nodes are inserted into the uplink graph, that is, all agents took an action. In the next execution of the learning algorithms, the rewards will be calculated and each agent will receive a specific reward. Some rules were defined during the action selection to increase the graph reliability and also to avoid cycle formation in the graph. So, the state will represent the destination of a message. For the uplink graph, the gateway will always be the destination. Each action available to an agent represents a pair of nodes available as successors. New actions will be created when new neighbors are available to that node. In these pictures, we can see the available successors for node 5 and the possible actions that can be selected during the graph construction. Positive rewards are given to the agent when the last action reduces its average latency. Average latency of a node is a measure of the time needed to data to be transmitted from the node to the gateway, and is also an average value of several latency measurements over a period of time, as stated in the paper. To evaluate our approach, we conducted simulations using a WirelessHART simulator over the NS2 environment. We also made adjustments in the environment to improve the energy and error models. Basically, we created scenarios that represent typical IWSN applications and the current literature. To have a generalization of the results, we used 30 random topologies and conducted 15 simulations for each random topology to get more information about the evaluated metrics. Each simulation ran by 12 hours of simulation time, where agents explored the environment in the first 8 hours and exploited by 4 hours. We measured the average latency of the network, the expected network lifetime, the packet delivery ratio, and the graph reliability in the last hour of each simulation. We then compared our approach with state-of-the-art algorithms, and we used analysis of variance to verify if the results are statistically significant. All the details of the methodology are also in the paper. Here we can see the average network latency. It's the average for all data sent over the network to the gateway over the 12 hours. We can see that the latency is higher during the network startup and exploration, and it stabilized during the exploitation phase. We can see that our approach presented the lowest latency when compared to the other routing algorithms for this specific topology. When using data from all the tested topologies, it can be seen that when compared to the baseline algorithms, our approach reduces the average latency in more of 90% of the 14 nodes topologies tested, and the average latency is reduced in almost 30% when compared to the Han algorithm. But, as our rewards don't take the energy consumption in account, it can be seen that the expected network lifetime is not increased in some topologies. More information about the results can be seen in the paper. So, about the conclusions, our approach reduced the overall network average latency in the topologies tested. It was not helpful in reducing energy consumption because of the rewards that we used. It slightly increased the packet delivery ratio. But when using this approach, we must consider the IWSN protocol used, since performance will be influenced by the protocol characteristics, like problems involving commands, times processed data, reconfiguration times, overhead, and so on. Also, the learning complexity and the states and actions defined must also be considered. Agents also influence each other and may cause problems. Future works can focus on evaluating other protocols, testing other reward definitions, and also trying to reduce the learning times. Another relevant work would be the development of a network manager with a building optimization model, and the development and comparison with other routing algorithms would also be interesting. Thank you for your attention. You can use these emails to send me some questions, and I will be available here to answer your questions right now. Thank you.